By now, we've absolutely squelched any remaining suspicion that you might have in your mind that the dark matter, evidence for which we found in the dynamics, the motions of galaxies and clusters, could possibly somehow be ordinary matter that was somehow hidden. It can't be gas or dust, because gas and dust would fall into clusters of galaxies, heat up, and we would be able to see it in X-rays. It also very probably cannot be ordinary stars, brown dwarfs, white dwarfs, neutron stars, or black holes, because those lead to microlensing events, which we've searched for and can't find. Finally, the real reason we know that ordinary matter in some hidden form can't be the dark matter that we have evidence for is both Big Bang nucleosynthesis and the cosmic microwave background put a very tight constraint on how much ordinary matter there is in the universe. It's only 5% of the critical density, but the dark matter is something more like 30%. We have to, in other words, turn to some unordinary kind of matter, some new kind of particle. So in this lecture, we're going to get serious and start saying, what kind of particle could be the dark matter? We have to go beyond the particles that we have already established exist in the standard model of particle physics. So what are the requirements for a new dark matter particle? Most obviously, it must be dark. The other important requirement is that it must be cold. So dark means not only is it hard to see, but it doesn't interact very much. When you look at a galaxy, the shiny part of a galaxy, the part that is easily visible from stars, comes from the ordinary matter, of course. The reason why the galaxy is able to contract is because ordinary matter interacts. Ordinary matter, in the process of collapsing under its own gravitational field, will get stuck. When one little bit of ordinary matter comes into contact with another one, it can cool off and settle down into the bottom. Dark matter seems to be distributed in a big puffy halo around the galaxy. It's not condensed right in the middle like the visible matter is. The explanation for this is very easy to come up with. It's that the dark matter particles just pass through each other and go right out. So dark matter needs not only to be dark, it needs to be not interacting with itself in any obvious way. The other requirement for the dark matter particle is it should be cold. In other words, even if the dark matter existed and had a small mass, but it were moving at a very fast velocity, if it were moving close to the speed of light in the early universe, then when it tried to collapse, it would go right outside and keep going. It would not oscillate back and forth like we want a real good dark matter particle to do. So we're trying to invent a new kind of particle that is dark and is cold. Let's just check that there's no such particle lying around in the standard model. Well, which particles in the standard model are dark? Of course, we don't want the ones that decay. Neutrons would not be good examples of dark matter particles because they decay away. You need something that will stick around. The only neutral particle in the standard model that is stable is the neutrino. Neutrinos are a very obvious place to look for a dark matter candidate. However, as it turns out, when you go through the details, because neutrinos are so light, they are not cold. When neutrinos decouple, when neutrinos freeze out from the primordial plasma at very early times, they're moving very, very fast. So they qualify as hot dark matter. If the dark matter we observe is hot, then structure on small scales in the universe doesn't form. You don't make galaxies in a universe which is mostly hot dark matter, because whereas the stuff would want to collapse, the neutrinos are moving out very, very quickly and tend to smooth everything out. Hot dark matter is actually quite strongly ruled out as a possible way for the dark matter to behave, so much so that these days we turn it around. We use cosmology to place a constraint on the mass of the neutrino. If the neutrino mass is too big, it would be the dark matter, but we know it can't be the dark matter because the dark matter is not hot. So that's a good way to get an upper limit on how big the neutrino mass could be. So that's the only possibility in the standard model of particle physics. We need to turn to particles beyond the standard model. So let's think of what the requirements are on those particles. Of course, they must be dark and must be cold. But in Lecture 9, we gave you an explanation for how to calculate the relic abundances of particles that are left over from the early universe. If a particle interacts strongly in the early universe, then the particle and its antiparticle will all annihilate away. And by the end of the universe's history, by today, we won't have anything left over. So what you need for a particle to be left over in sufficient amounts to be the dark matter is a particle that does not annihilate very strongly, a particle that is weakly interacting. Now, when we say weakly interacting, you might think, and it might be perfectly sensible, not interacting very much. It doesn't interact very often when two particles come together, and that's true. But now let's actually plug in the numbers. Let's do our calculation of what kinds of particles give rise to the right abundance of a particle today to be the dark matter, and ask how often should particles annihilate in order for them to be good dark matter candidates. The answer is that the right rate of interaction for a new particle to be the dark matter candidate is exactly that it would have if it interacted through the weak nuclear force. So when we say weakly interacting particles are good dark matter candidates, we don't simply mean particles that don't interact very much. We mean particles that interact via W and Z bosons, particles that interact via the weak interactions of the Standard Model. It's not the only possible way to get dark matter, but it's suggestive. It's telling us that if we invent a new particle that is stable, that is not interacting through electromagnetism or the strong interactions, but does interact through the weak interactions, it is a natural dark matter candidate. So the name attached to such a candidate is a weakly interacting massive particle, or a WIMP, as opposed to the machos, which are the compact collections of ordinary matter. So we want to make WIMP candidates. We want to make new examples of particle physics that give us weakly interacting massive particles that are stable and could be the dark matter. For most of this lecture, what I'm going to do is talk about one specific example of a particle physics model that naturally leads to a candidate WIMP dark matter particle. This specific example is called supersymmetry. But really what you should be getting out of this lecture is not the details of supersymmetry as a candidate way to get dark matter. It's just an example of the kinds of thought processes that physicists go through when they're trying to invent new particles. The point is that you don't want to just say, well, yes, there must be some particle and it's the dark matter. Particles have interactions. Particles come with different properties. We know a lot already about the particle physics of the Standard Model, so when you're inventing a new particle, it has to fit in somehow. The best dark matter candidates will be those that have some natural interpretation in terms of particle physics all by themselves, even if we didn't know that there was such a thing as dark matter. Supersymmetry is an excellent example of that, and that's why it's worth going into it in some detail. So supersymmetry is a hypothetical idea which invents a new symmetry onto the symmetries we already know about in the Standard Model. We already mentioned that the Standard Model of particle physics is characterized by a great amount of symmetry. For example, the most obvious thing that you see in the Standard Model is that when you look at the fermions, they come in three generations. You have the up and down quark in a doublet, the electron and its neutrino in a doublet, and all by themselves, those four particles form a self-contained set. Then you have another four particles which repeat that pattern, two quarks and two leptons, the charmed and strange quark and the muon and the muon neutrino. And then it happens yet again with the bottom quark and the top quark, the tau and the tau neutrino. So the fact that you have a similar structure repeating itself over again is an example of a symmetry. And at a deeper level, symmetries are responsible for the forces between particles, the strong nuclear force, the weak nuclear force, and the electromagnetic force. So supersymmetry is a very specific kind of symmetry, a different kind of symmetry than we have ever seen in the Standard Model. It's a symmetry that relates bosons to fermions. Bosons are the force particles, the particles that can pile on top of each other to give rise to electromagnetic fields, gravitational fields, and so forth. Fermions are the matter particles. They're the particles that take up space. These seem very different from each other. Remember, there's a thing called spin, and bosons always have an amount of spin that is 0, 1, 2, etc. Fermions always have an amount of spin that is 1/2, 3/2, 5/2, etc. So supersymmetry is a speculative idea. It's saying that somehow there could be a symmetry relating particles of different amounts of spin. If that is true, the nice thing is that you can have a lightest supersymmetric particle, which is a perfect dark matter candidate. Such a particle is sometimes called the neutralino, and that's what we want to explore here. So if supersymmetry existed, for every kind of fermion particle, there would be a boson particle with the same kinds of charges and the same mass. And vice versa. For every boson, there would be a corresponding fermion. So for example, you have a bosonic particle that has a certain mass, a certain electric charge, a certain interaction under the weak nuclear force and the strong nuclear force. If supersymmetry existed, there would be a fermion with the same mass, the same electric charge, the same weak and strong nuclear force interactions, but a different spin. Now you can look in the Standard Model. There are certainly particles of both kinds of spins in the Standard Model. There are bosons and fermions, but they certainly don't match up. You can't take the bosons of the Standard Model and say, well, for this boson, this fermion is obviously its superpartner. It doesn't quite go like that. You could also imagine that there are new particles. There are particles that we don't see in the Standard Model yet, but that could be the superpartners of the particles we know and love. For example, the electron would have a partner that was a boson, and it would be called the selectron. It would have a charge of -1, just like the electron does. It would have a lepton number of +1, and it would have a quark number of 0. It would not interact with the strong interactions, but it would interact with the weak interactions. But if supersymmetry were exactly right, that selectron would have exactly the same mass as the electron, and that's clearly not true. If there were a bosonic particle with the electric charge of the electron and the same mass of the electron, we would have noticed it long ago. So somehow we have to invent a whole new bunch of particles we have never yet seen. What we have done is we've given them names. That's a good first start. If we haven't actually found them yet, at least we can come up with their names. The new particles that we need to imagine, if we're going to believe that supersymmetry is right, are the fermionic partners of the existing bosons and the bosonic partners of the existing fermions. The bosons that are the partners of the existing fermions are given names that are derived by tacking an S onto the beginning of the name of the fermion. So we have different kinds of quarks, for example. Their bosonic superpartners are called squarks. We have different kinds of leptons. Their bosonic superpartners are called sleptons. So you have the electron and its partner the selectron, the neutrino and its partner the sneutrino, etc. You can have great fun with this if you go very far. For the existing bosons, they have fermionic partners that are given names that you get by tacking the suffix ino at the end of the particle name. So you have, for example, the photon, which is a boson. It has a fermionic superpartner called the photino. The graviton is a boson. There's the gravitino fermion. The Higgs boson we think exists has a partner called the Higgsino, and so forth. So you get all sorts of particles. If supersymmetry is right, given the fact that there is no way to match up the particles we already observe, supersymmetry is hypothesizing that we have doubled the number of particles in the real world than we have actually observed in the Standard Model of particle physics. So it is a very economical idea in the sense that it's just one little idea. Just say there's a symmetry between bosons and fermions. That's easy to say. But it becomes very prolific in terms of what kinds of particles it predicts. It's not just one more particle tacked onto the Standard Model, it's doubling the number. Now you might ask, is it worth doing that? Why are we contemplating doubling the number of particles that we have in nature? Well, dark matter is a nice benefit from inventing supersymmetry, but it's not the primary motivation. In fact, the very first reason why supersymmetry was invented is because it is predicted by string theory. String theory, which is something we'll discuss later in the course, is a hypothetical way of quantizing gravity, and it turns out that string theory only works if you have supersymmetry. That's why supersymmetry was invented. But then it was recognized that even if string theory isn't right, supersymmetry by itself is not only aesthetically pleasing, it's not only a very nice and elegant symmetry of nature, it also solves some naturalness problems that exist in the Standard Model. The foremost one is called the hierarchy problem. We're not going to go into great detail about the hierarchy problem, but it's basically the fact that the different mass scales of particle physics are very, very different from each other. That is the kind of thing that particle physicists don't like. They don't like things to be very, very different from each other unless there is some good reason. So the mass of the Higgs boson in the Standard Model of particle physics, which is the thing that sets the mass scale for all the massive particles in the Standard Model, is somehow very, very different than the high energy mass scales we're familiar with from gravity, from the Planck scale, or from grand unification theories. So why is the Higgs boson so much lighter than the particles that we would expect to exist at very high energies? That's called the hierarchy problem. Turns out that in supersymmetry, there's a natural explanation for the hierarchy problem. That's why most particle physicists like supersymmetry as a candidate for physics beyond the Standard Model. The problem, of course, is that we don't see selectrons, we don't see squarks, etc. somehow they must be hidden from us. In particular, they must weigh a lot more. They must have a much bigger mass than we would naturally expect. How do you do that? The answer is that this symmetry you're inventing, supersymmetry, must somehow be hidden from our immediate view. The idea that symmetries are hidden is a very familiar one in particle physics. In fact, it's the correct way to think about the weak interactions. We mentioned that the W and Z bosons that carry the weak interactions are very heavy particles, unlike photons, gluons, and the graviton, which are very light particles. Why is that? In their natural state, the W and Z bosons that carry the weak interactions would be massless. But it turns out that the symmetry associated with those particles is broken by empty space. In fact, by the Higgs field. That's why the Higgs field must exist. The role of the Higgs field is to break the symmetry of the weak interactions and give mass to the W particles and the Z particles. This sounds like maybe cheating. You're trying to sort of hide something in a broken symmetry to explain things you don't otherwise understand. But the idea that properties of particles change depending on where they are or the medium through which they move is very natural. For example, light does not always travel at the speed of light. The speed of actual light rays is different in air or in water or glass than it would be in empty space. That's because the medium through which the light is traveling has properties all by itself. So when we speak of the speed of light, we really mean the speed of light in vacuum. But in stuff, the speed of light can be very different. Similarly, the idea of a broken symmetry is that some field pervades empty space. Modern particle physics says that even in empty space, there is a Higgs field, something that has a non-zero value, and the reason why W and Z bosons have mass is that they're traveling through this Higgs field. That's a very successful idea. The particles that were predicted by this idea have largely been discovered, and Nobel Prizes have been given out. So we just want to do the same kind of thing, but now we want to do it with supersymmetry. We want to break supersymmetry. There wants to be some mechanism that breaks that symmetry at a deep level. If that happens, then all of the superpartners of the particles in the standard model become heavy. So basically you take a whole bunch of particles that had the same masses as the particles we observe, but you lift their masses by a large amount, you raise them by breaking the symmetry, and you end up with a whole bunch of particles, all of which are very, very heavy, at least 1,000 times the mass of the proton. So the reason why we haven't discovered supersymmetry yet in this scenario is that it's just too hard to get there. It's just out of our reach, although we're trying to do it right now. So an interesting wrinkle of this possibility is that there can be a new conserved quantity associated with supersymmetry. Remember that there are things called quark number, lepton number, electric charge, which have a quantity that can neither be created nor destroyed. An electrically charged particle cannot decay into neutral particles. Well, what if superness is also a conserved quantity? What if whether or not you are in the standard model or a superpartner of the standard model is a conserved quantity? Then the superpartners of the standard model would not be able to decay into the partners we see, into the actual particles that we know exist in the standard model. So therefore, the lightest supersymmetric particle would have to be stable. There would be nothing for it to decay into. So what we're saying is that there would be a kind of particle that would be stable because it carries some conserved quantity. It is heavy. It's 1,000 times greater than the proton, so we haven't seen it yet. And it can very plausibly be weakly interacting. These are particles that are part of the supersymmetric standard model. They're not completely separate. So you could have particles like the partner of the Higgs boson would be the Higgs xeno. That would be an electrically neutral particle, but it would feel the weak interactions. Likewise, the xeno, the partner of the Z boson, or even the photino, the partner of the photon. These would all be massive, possibly stable particles, any one of which is a candidate for the lightest supersymmetric particle. Any one of them would make an excellent WIMP. They are all weakly interacting massive particles. We don't know which one is the right one because we don't know which one is lightest. Under different scenarios of supersymmetry, different particles are going to get different masses. So that's one of the things we need to figure out by taking data. We're not going to know until we do experiments and find the superpartners which one of them is actually the lightest, which one is the LSP, the lightest supersymmetric particle, or the neutralino. So the reason why we like this theory is because supersymmetry was not invented to give us a dark matter candidate. It was invented for other reasons, but lo and behold, a perfect dark matter candidate pops out. It's easy in supersymmetry to get particles that are stable and weakly interacting and massive. So what you want to go do is test this idea. You want to go look for these particles. So there are various ways to go look for them. The one that is sort of the most promising over the next few years is called direct detection, which is build an experiment which will actually find a dark matter particle directly. The problem is dark matter particles by construction are weakly interacting. They don't interact very much. So what you have to do is very similar to what has already successfully been done with neutrinos. You need to build a detector that is deep underground, shielded from the noise that we're subjected to here on the surface of the Earth, and is very, very sensitive to particles coming in and lightly glancing off of an atomic nucleus in the detector. We've already done this for neutrinos, but neutrinos are, number one, at a very different energy scale than the dark matter particles are, and number two, there is a shining beacon in the sky that emits neutrinos, namely the sun. For dark matter particles, what we're looking for is a background of dark matter particles. We don't have a shining source to look at, so it's harder to do. But there's a number of experiments going on right now that are actively trying to do exactly this. It's very plausible that over the next couple of years, there'll be a headline in the newspapers in the morning saying scientists have directly detected the dark matter of the universe. But maybe they won't. You don't know. That is a hard thing to do. In different models, it becomes very easy or very difficult. So we're trying other ways. One other way is a very clever idea, taking advantage of the fact that not only do you have dark matter particles, you have dark matter antiparticles. The reason why the dark matter particles have a certain density is because they have stopped annihilating because the universe has expanded. They have both particles and their antiparticles in the dark matter. They just don't annihilate because they don't interact with each other. There aren't that many of them around. There aren't that many dark matter particles per cubic centimeter. Much like neutrinos, they can pass right through each other very easily. You need a very high density of dark matter particles before you would begin to see them annihilate. But there are places in the universe where the density of dark matter particles might be very high. At the center of a galaxy, or at the center of clusters of galaxies, the dark matter particles that were very spread out will collapse. They will contract and they will gather in the same place, and there you will begin to see dark matter particles annihilating with dark matter antiparticles. When that happens, they're going to give off radiation. They're going to give off high energy photons, and in most models, what they will give off are gamma rays. Gamma rays are hard for us to observe here on Earth, because if a gamma ray from the sky comes to us here, it will be absorbed by the atmosphere. So NASA and the Department of Energy are building a new satellite called GLAST that will be launched in 2007, and GLAST is going to be looking for gamma rays at the centers of galaxies and the centers of clusters of galaxies. What that means is we will be indirectly detecting dark matter. If we see a signal of gamma rays from a very specific source at a very specific energy, that is exactly what you'd expect if a particle and its antiparticle were annihilating. Again, this may or may not happen in different models. We have to go out there and do the experiment to see if nature is being nice to us in this way. Finally, we have perhaps the most direct method of all, which is that forgetting about the dark matter that is surrounding us, let's go and make our own dark matter. This is what particle physicists are paid to do, to collide energetic particles together and to make new ones. This is what we're trying to do right at this moment, and we're building better particle accelerators to do even better. The reason why it's not a surprise that we haven't yet made dark matter particles is because it's hard to notice even if we do. Dark matter particles are weakly interacting, so they're very hard to make, and they're neutral, so they're very hard to detect once you've made them. In other words, we might be making dark matter particles all the time in current particle accelerators, but we just don't have enough data to be sure that that is what is going on. As of 2007, the most high-energy collisions that we can produce here on Earth are being produced at the Fermi National Accelerator Laboratory, or Fermilab, outside Chicago. They're making high-energy collisions at about 1,000 times the mass of the proton, at about the place you would just expect to see superpartners beginning to be created. The problem is, since it's just at the edge, you might make one or two and you would never know. So we're crossing our fingers. It's certainly possible that the Tevatron, the accelerator at Fermilab, could make supersymmetric particles, but we can't guarantee it. Therefore, we're trying to build even better accelerators. The Large Hadron Collider is being built right now at CERN, a European particle accelerator outside Geneva. It is scheduled to turn on in late 2007, but it will take at least a year for the energies to ramp up. Once they do ramp up, the energies at the Large Hadron Collider, the LHC, will be 10 times more than the energies at Fermilab. We'll be able to create vastly new numbers of particles at the LHC that we could only barely hint at the Tevatron. So it's, again, very, very plausible that just a couple of years after the accelerator turns on, we'll be awash in supersymmetric particles. The problem there will be there'll be too many of them. We'll have to figure out what is going on. This is not going to be an overnight project, but it's going to be a lot of excitement involved when we discover new particles at the Large Hadron Collider in trying to make sense of them, trying to figure out how these new particles fit into particle physics, whether or not one of them could be the dark matter. It's also possible, of course, that there is dark matter, that the dark matter is some neutral particle that does not interact very strongly, but that does not come from supersymmetry. So there are candidate particles for dark matter, both that qualify as WIMPs, weakly interacting massive particles, and other kinds of dark matter particles. So I'll give you one example of a particle that is a different way to get a WIMP, a particle that is neutral, stable, and feels the weak interactions. That's something called the lightest Kaluza-Klein particle. This is an idea that has nothing to do with supersymmetry. It says that there are extra dimensions of space. There are tiny directions that you can go in space that are curled up into little balls so that you can't see them. This is something we'll talk about in some detail in the last few lectures of this course. But the point is, if you have tiny curled up dimensions, then every particle that we already know and love, electrons, photons, and what have you, have an infinite number of partner particles that correspond to particles that are moving in the extra dimensions with different amounts of momentum. Because of quantum mechanics, these different amounts of momentum are not arbitrary, they're quantized. So there is a minimum amount of extra energy that a particle can have from spinning around in the extra dimensions that would show up to us as something called the lightest Kaluza-Klein particle. It could very easily be weakly interacting and massive. That's another very promising candidate for a WIMP and therefore for the dark matter. Then there are also particles that are not weakly interacting at all. In other words, they're the dark matter, but they don't feel the W and Z bosons. One example are neutrinos, but sterile neutrinos. A sterile neutrino is exactly a neutrino that doesn't feel the weak interactions. That's what the word sterile means in this particular context. So you can invent new kinds of neutrinos. Neutrinos already don't feel the electromagnetic force or the strong nuclear force. These are a kind of neutrinos that don't feel electromagnetism, the strong force, or the weak force. All they feel is gravity, and they can occasionally interact with other kinds of neutrinos. So people are making models of massive sterile neutrinos, calculating how many you can make in the early universe, and it's easy to get the right abundance to be the dark matter. The only reason why this kind of model is not as popular as supersymmetry is that you don't get a lot extra out of it. The bonuses that you get from supersymmetry are quite considerable just from the particle physics perspective. Sterile neutrinos help you a little bit, but we don't know whether they're part of some bigger picture yet. Finally, let me mention axions. Axions are perhaps the second leading candidate for dark matter particles after supersymmetric particles. But axions are really completely different in conception than supersymmetric, the LSP or the neutralino would be. Axions are bosons, whereas the supersymmetric particles that would be the dark matter are fermions. The supersymmetric particles are very heavy, 1,000 times the mass of the proton. Axions are very light. Axions have the same kind of mass that a neutrino has. They're very, very low mass particles, which ordinarily you would expect would be fast moving. Neutrinos can't be the dark matter because they're so light, they're moving very fast, and they do not make good dark matter candidates. Why is it that axions, which are very, very light, can nevertheless be cold dark matter? The answer is the axion is created by a very different mechanism than neutrinos are or WIMPs are. The axions, in the models that people write down, were never interacting with the rest of the particles in the plasma of the very early universe. They were never heated up by interacting with the rest of the stuff in the primordial soup. Instead, there was a kind of field, an axion field, that didn't change. It was just stuck there, and it contained energy. This energy was just constant. It wasn't going away until a phase transition happened and this field melted. When this field melted, it went from being a constant amount of energy per cubic centimeter to a bunch of axions. The field melts into a bunch of axions with zero velocity. A completely different mechanism than you get for making weakly interacting massive particles or neutrinos. It turns out that there are enough free parameters in the model to make this kind of axions from a melting field with exactly the right kinds of density to be dark matter. So this is good news and bad news. It's good news because it's a completely different way to get dark matter particles. The bad news is that therefore the ways to go and look for axions are completely different also. The kinds of experiments we're doing to try to find WIMPs in underground detectors, in the sky, and in the laboratory have a set of corresponding experiments we would like to do for axions, but they're different experiments. So people are still doing those experiments. We're very hopeful that we'll find either WIMPs or axions. We might even get especially lucky. The best universe, if you're a theoretical physicist, would be one in which half of the dark matter is supersymmetric particles, half of it is axions. We'll actually have to do the experiments to see whether nature is so kind to us as that.